This afternoon, I'm recording the second micro lesson. I'll be talking about a very difficult topic called critical acceleration. So let's first take a look at what exactly critical acceleration is. Let's look at this example problem on the left. It's known that this is a wooden block with a mass of capital M. On top of it is an object with a mass of lowercase m. Also, it's known that the ground is smooth. Then lowercase m is subjected to a horizontal pulling force to the right, R, but between capital M and lowercase m, there is friction between them, and it's known that their coefficient of kinetic friction is mu. Also, in this case, we can also consider the maximum static friction to be equivalent to the kinetic friction. So, based on the problem statement, we can derive the maximum static friction between lowercase m and capital M. R, which is equal to the kinetic friction between lowercase m and capital M. So that's mu R, the friction between the two. What should that be? It should be mu times lowercase m times g. Now, let's set this problem aside for just a moment and take a little time to think about it. Let's say, for example, in real life, you encounter a problem like this. Take a moment to think about it. What if f is actually very large? Then when f is extremely large, what will happen? Won't the extremely large force F simply pull the small m away very quickly? In other words, what will happen between the two objects is that relative sliding will occur. Or in other words, the two objects will each move independently, right? But when F is relatively small, the two will move together to the right with uniform linear acceleration. So why does this happen? Where is the critical point? At what point will the two separate? Let's take a look together. So let's first analyze the case where the force F is relatively small. When F is small, as we said, they don't separate. So we can analyze the forces on them as a whole system. Their acceleration is the same. So analyzing the forces on the whole system, what horizontal force is acting on it? Since the ground is smooth, the total net force is just capital F. So let's write out Newton's second law for the whole system. Then we can analyze the forces on one of the objects. Either one is fine. So for example, we can choose to analyze the forces on capital M. So why is it that the large M gets an acceleration to the right? It's because we know that the small m gives this large m a what? The small m gives the large m a force to the right. What kind of force is it? Static friction. Of course, this small m will also experience a static friction force to the left. This is a pair of action-reaction forces. Okay. So through force analysis, we can determine which force is providing the acceleration for the large m. Hey, it's the static friction that the small m provides. So for the large m, we apply Newton's second law. That is, hey, the static friction provides its acceleration. Now let's take a look at these two formulas together. When F is very small, then this A is also very small, right? So if A is small, my static friction is also small. No problem, the static friction can be that small. But as F increases, then their overall acceleration will also increase. Then the acceleration of the large m will also increase. So the static friction required by the large m will also become larger and larger. But the problem has already stated that between the small m and the large m, there is a what? There is a maximum static friction. So students, think about it. When A reaches a critical point, doesn't this static friction reach the maximum static friction? So reaching this maximum static friction means that this maximum static friction can provide its maximum acceleration, and so the critical point can be found. If at this point this F increases further, won't this large m be unable to keep up with the acceleration of the small m? What will the two of them do? They will separate. So we have now found that critical point. That critical point, how many conditions does it satisfy? It satisfies two conditions. The first condition is At the critical point, they haven't separated yet, but are about to. So their accelerations are still the same. We can still use the whole system method to analyze their forces. The second point, the friction between the two objects has reached what? It has reached the maximum static friction. Okay, so for these two equations, we still have the first equation is F equals large m plus small m times a, the whole system method. The second is that its static friction has reached what? The maximum static friction, and the maximum static friction is mmg. Provides the acceleration for the large m. So in these two equations, F is unknown and a is unknown. By solving these two equations simultaneously as a system, we can find the values of a and f. This is the critical acceleration and critical force for two objects to be able to move together with a common uniform acceleration. What does that mean? Let's take an example. For instance, let's assume the critical acceleration I calculated is 4. The critical force is 20 newtons. So students, if F is less than or equal to 20 newtons, then what will the two of them do? They will accelerate uniformly together. So what if F is greater than this 20 newtons? In that case, what will the two of them do? They will move separately. What will happen? They will separate. So including this connected acceleration of two objects, like the plate model we discussed, also involves an examination of this problem. Okay, so this is the origin of this connected acceleration. When we encounter this type of problem, we must first find the critical point R and calculate this critical force and critical acceleration. Then determine whether the objects are accelerating uniformly together or have already separated, and then proceed to solve the problem. So corresponding to this, I have also found two problems for you from our Beijing, two problems that have appeared on exams before. Everyone, take a look at this one, the second one. The second one is a ping pong paddle. It's supporting a small steel ball with a mass of 0.1 kilograms. It is known that the angle of this ping pong paddle is 37 degrees. The ping pong paddle is rough. Of course, in that problem, an athlete was holding this ping pong paddle, and at that time, the mass of the ping pong paddle was also given. So now they are supporting this steel ball and moving with an acceleration equal to 5 meters per second squared to the right with uniform acceleration. What are we asked to find? Find this steel ball's the magnitude and direction of the static friction force it experiences. Okay, now students, think about it. Can we find their critical point in this situation? The critical point. Let's do a force analysis. First, let's analyze the forces on the small ball. The small ball is definitely subject to a gravitational force. It is also subject to a vertically upward support force. So everyone, think about it. Is this steel ball necessarily subject to friction? Is it possible for its friction to be directed downwards? Or is it possible for it to be directed upwards? All three situations are possible. Therefore, we are currently unable to determine the direction of this static friction. Therefore, through my analysis, you should have found that there is a critical state. What is this critical state? It's when there is no friction acting on it. What would the acceleration be then? Right? So if there's no friction, what forces are acting on it? Only gravity and the normal force. All right, let's take a look. Let's combine them. This is specifically the net force acting on the small ball in this situation when there is no friction. Right, so let's calculate the net force, 37 degrees. So what can we conclude the net force is equal to? It's equal to mg times the tangent of 37 degrees. It equals m times a, equals m times a. So we can find by cancelling out m, what does it equal? The tangent of 37 degrees is 0.75, so it equals 7.5 meters per second squared. What does this mean? Isn't this acceleration precisely the one when the steel ball is not subject to any friction? It's critical acceleration. Okay, now let's look at the problem. What does it say? Its current acceleration is what? 5. So isn't 5 smaller than this 7.5? If it's smaller, everyone, think about it. In that case, in which direction should the friction on the steel ball be? Shouldn't it be upwards along the incline? So when A is less than this 7.5, when it's less than 7.5, I can't use that. My net force is already too large, right? So the static friction it should experience at this point is upwards along the incline. So for this problem, it is subject to a static friction force upwards along the incline, okay? It's subject to a normal force and gravity. Then you can just use force composition and decomposition to solve it. Conversely, when a is greater than 7.5 meters per second squared, then at this point, relying solely on gravity and the normal force is not enough to provide this acceleration, right? So what do I need? A static friction force directed diagonally downwards to the right to help you. In this way, we can analyze this problem clearly. This is the second type of situation. So let's take a look at this problem, example 3. This example 3 is also an old problem from Beijing. So this is a smooth inclined plane, and on it is a small ball with a mass of m. What is the angle of inclination? It's 30 degrees. The entire system is undergoing uniformly accelerated linear motion with an acceleration to the left. What are we asked to find? We need to find the magnitude of the tension and the normal force on the small ball. So students, think about it. Just think about it. The entire system is uniformly accelerating to the left. When the acceleration is relatively small, isn't this small ball still on the inclined plane? But when its acceleration is very large, what will happen to this small ball? What will the small ball do? It will leave the inclined plane, and so to speak, it will float up. Therefore, we have found the critical point of this problem. What is it? The critical point is when I'm still on the inclined plane, but I haven't floated up yet. At the same time, the small ball and the inclined plane have just lost, there is no normal force, right? If the acceleration exceeds this point slightly, if it's a bit larger, it will float up. If it's a bit smaller, won't there be a normal force from the inclined plane? So, okay, now that we've found the critical point, let's do a force analysis on it. What forces are acting on it? There's the force of gravity along the direction of the string because it hasn't floated up yet. There's a supporting force along the direction of the string. Okay, the composition of our net force is done. Composition. The net force of gravity, right? So we can conclude that at this point, the net force at 30 degrees is equal to the square root of 3 times mg, which equals ma. So we can find that its critical acceleration is the square root of 3 times g, with the direction being horizontal to the left. Now, students, think about it. If my acceleration is greater than the square root of 3g, if it's larger, won't it float up? Students, for example, 2g. Let's say A is 2g. So it floats up. Since it floats up, we can't use the 30-degree angle, right? So I need to redraw it. It floats up. It floats up, so I'll draw it floating in this position. I don't know this angle. We don't know what this angle is, but that's okay. What forces are acting on it? There's gravity and the tension from the string. The net force of these two forces provides, the acceleration. The gravity is constant. The net force, isn't the net force equal to ma? So this is 2 mg. then the angle and the pulling force can all be calculated. So this is the first scenario. Now, students, think about it. What if the acceleration is less than the square root of 3 times g? If it's less than the square root of 3 times g, then students, think about it. At this point, it hasn't lifted off. So at this time, it's still on the inclined plane, but it is subjected to gravity, the pulling force, and the support force perpendicular to the inclined plane pointing upwards. Okay, so I just perform force composition and resolution on it, and then I can calculate the pulling force and the support force. All right, so this first type of problem involving the pulling force and reaching the critical state of maximum static friction and the critical acceleration is something that for first-year high school students is a key and difficult topic that often appears on exams, and the error rate is also quite high. So as first-year high school students, you must master this key and difficult type of problem. Now, as for the second and third scenarios, these are in the file I sent to everyone, the one I shared in the group chat called, I've compiled 6 special topics like critical acceleration and so on. There are problems like these in there. Everyone should find it and work on them. You must strive to master Chapter 4, Newton's second law, which is a particularly important and difficult topic.